Right, Lucas, we are ready for you now. Right, Lucas has also been helping us here with TUB. And yes, I'll let you take your presentation. Right.
So thank you, Kyle. Hello, everyone. The next topic is going to be a little bit more theoretical, more from the university and research side, which I know can be hard just before the lunch break, but I'm trying to keep it as little theoretical on the mathematical side as possible. I'm going to tell you a little bit about something concerning superstructure optimization and what we're currently doing research on, and how all of this is connected to CAPE-OPEN in the beginning. So motivation, background, what is process synthesis? Where is process synthesis aligned with, for example, design and construction? Well, you usually do it right in the beginning of envisioning the process. So what you want to have is a very broad search space of possible processes that you want to investigate. So in order to really cover all of this search space, a proper superstructure optimization approach usually has to have a certain set of three, let's call it attributes. And it first of all has to be very general, because we want to have an approach where we can, for example, put separation processes, reaction processes, and so on into it. And then at the end, when we say, okay, we want to, for example, separate a process stream into certain components, we don't want to specify what kind of unit operations to use in the best case, but we want to have an approach that is as general as possible. Do we want to use maybe vapor-liquid separation? We want to use membranes? I don't know. Let's have this optimizer decide that. So generality is an attribute that has to be there. On the other hand side, we opted for an approach of rigorous thermodynamics. So it has to be quite precise, because we want to retain precision inside of the superstructure optimization. We don't want to abstract to data-driven approaches, but we want to really stay rigorous in thermodynamics in order to get rigorous models out of our modeling approach that depict reality quite precisely. And the third part, we label it as tractability, basically boils down to whether a process is physically valid or not. If we have a separation unit with no inputs but two outputs, that doesn't make sense. So tractability really means, do we have a process that we can follow? Do we have a process that makes sense in the physical case? So stitching all of this together, previous colleagues of mine already did a lot of work on this field. And what they developed was a sort of framework pipeline where we're now using these building block-based approaches to retain the generality I was just talking about. Here we can see a separation column divided into two of these building blocks. Now, this would be the case for vapor-liquid unit building block. And from there, these models can then directly be implemented into our in-house tool, mosaic modeling, which you've heard about from Erik beforehand. And the nice thing about mosaic modeling now is that we can abstract in this modeling environment these unit operation blocks. So what you can see in the middle is the abstract representation of the left-hand side column configuration with a distribution network, it's called, which ultimately decides where a process feed coming in from the left should be directed to. Should be directed to vapor-liquid unit 1 or vapor-liquid unit 2. And from there, from the outputs of this vapor-liquid unit, where should they go? Should they be sent into the output directly? Should they be recycled? And so on. So we have this abstract representation. We have a very general representation of our actual problem, of our separation problem, with these building blocks. And these can now be represented in mosaic modeling explicitly. From there, we as modelers can then decide where we want to have this code exported to, where we want to solve this problem that we have now abstracted into this very tractable view, but not quite physical to solve. So from there we go to code export, and there was work done predominantly in GAMS from our work group, where this model is then exported and solved. And we've been talking about fidelity and precision. In order to solve these rigorous thermodynamics, we needed a way to actually access these. And the method and tool of choice was to use T and CAPE-OPEN as thermal property package and manager, therefore, to use inside of GAMS. Since this capability was not envisioned before, they had to a wrapper had to be developed, which is then implemented in C++ as a DLL, which is all exported by Mosaic modeling. Yeah, the basic code structure is there in Mosaic modeling, and it's exported alongside with the GAMS code in order to assure that both of these models are compliant, such that I have a model on the GAMS side, which then does the right thermal function calls in T, gets them from CAPE-OPEN, and can work with these. Also, code that was worked on, not directly exported from Mosaic, but very much needed, is the part of tractability, where we perform a graph analysis on the MATLAB side in order to assure that, as I said, the networks that we're proposing in the solution approach are actually physical. There's a set of rules behind, as I was previously mentioning, a unit operation with no inputs cannot have any outputs, and therefore this setup does not make sense. There's a couple of other rules underlying here. And so this is what's been done. What's there to work on? Well, these superstructure problems tend to increase in size very rapidly. The more unit operations you put into the problem, the larger the whole thing gets. Essentially, when relaxing or when using means of relaxation, the amount of constraints also increases and the amount of variables increases. So the problem gets large very fast. Colleagues were able to solve these sort of problems with the realm of 4 to 6, sometimes even 8 unit operations, but it would be nice to have a larger amount of unit operations at hand, and also a mean of deciding whether we need certain unit operations or not. So a mean at hand to basically deactivate unused unit operations in the solution process. So the challenges that arose were essentially solution time, because increasing the scale increases solution time. So if we can decrease solution time, we can increase the scale. Also, the initialization of these unit operations is quite difficult topic when we speak about generality, and we all of a sudden have a totally new flow sheet. How do we initialize this flow sheet? Yeah, so these are problems that arose. And tractability, as I just said, it would be nice to activate and deactivate these sort of unit operations in order to not have them at all on the flow sheet, but we don't need them. And the way to go, since we are rigorous and we want to stay rigorous, was how about we explore the space of so-called GDP, Generalized Disjunctive Programming. What GDP is, in the basic view, it's just another representation of our MI-NLP problems that we all know. Yeah, we can start out by a logic formulation of the problem that we have. For example, do we want to take the one splitter or the other, which would be represented by a logic variable, true or false. And then over the course of modeling, we reduce it down to binary variables, relax them to algebraic variables, and then we solve that. GDP, basically on the most abstract level, wants to retain this logical structure for as long as possible. It does not want to relax very fast, but it wants to take advantage of the logic structure of these problems. For example, you can see in the formulation, these disjunctions, they have an AND symbol and this Yij inside of it. And this Yij is now a logic variable, can be true or false. And what this representation basically means is if Yij is true, then the set of constraints Gij is inside of our model. If it's false, it's not part of the model. So by that, we can basically think this to the end. We can decrease the size of our equation system by, for example, not including on the right-hand side certain unit operations. So this is the idea behind it. Of course, during the course of solution, for example, if you look at the branch and bound algorithm, at some point you want to fix these logical variables. And if you have fixed these logical variables, you can then not include these sets of equations. That's the idea behind it. Another very nice idea behind generalized disjunctive programming is that since we retain the logical structure of the problem and do not relax ourselves, we can leave the relaxation to an algorithm that we can specify. For example, Pyomo has a very, very neat tool called Solver Factory, where you can just input your GDP problem and then choose the relaxation method that you want to use. Yeah, so it takes away the quote-unquote burden of having to do this manually and leaves it to an algorithm. So you as a user can way more freely explore spaces that might otherwise be untouchable by retaining this logical structure. But one more thing, which was also shown in the past, is that you can use this logical structure now to build dedicated algorithms. You can now use the logical structure to derive, for example, so-called logic-based branch and bound algorithms, which take advantage of the logic structure and push the relaxation to a later stage in the algorithm. So for example, if you have a subset of non-relaxed binary variables or non-relaxed logic variables now, but you have a set of relaxed variable, non-relaxed variables or fixed variables, you can now take equation systems out of the mix that are, for example, disabled, and then relax the remaining problem. So you can push the relaxation to a later stage, and by that, decrease solution time. So this is the theory behind of it. It's working in theory better. It's a better relaxation. So we started out, what do we need in order to make this all happen? So I've been talking about mosaic modeling, and this is the method of choice. This is the tool of choice, because we want to use mosaic modeling as a central part inside of this whole solution architecture. Why? Well, because we have a very abstract representation of our models already. So if you, for example, want to have different sets of equation systems active, well, we could just export different sets of equation systems directly. So this is why we opted to develop in mosaic modeling. And where we're currently at, you can see on the left-hand side, this would be the optimization problem as it comes from a generic example. Yeah, you have this objective function, you have the disjunction equations, and you have so-called logic propositions. They are global rules. For example, if I have a reactor, then afterwards there should be a flash. Then I can say, okay, if the logic variable A is true, then B has to be true as well. And from there, we're now in the stage of model development, where we can now abstract this model as it comes to our mosaic modeling environment, and from there directly generate code in dedicated programming platforms. Yeah, tried this out yesterday. Wanted to calculate a problem that came in a paper. Took me 20 minutes to export GAMS and Pyomo code and prototype it. So this pipeline, it works. Works quite nicely, quite neatly. So what are the caveats currently? Well, if we're looking at where we want to go, which is use CAPE-OPEN and COBIA inside of this solution architecture, we really need to be able to perform external function calls. And this is where, for example, GAMS currently has problems with its out-of-the-box functionalities. There's the idea of developing in-house branch and bound methods for that, for example. But it turned out that GAMS is not currently available to do this. So we switched to Pyomo and are currently developing our new architecture in Pyomo, where we then perform external function calls to COBIA, where we do have the architecture set up for our C++ wrappers, which now are pending the connection to the Pyomo framework. Okay, so I hope this wasn't too much. I'm done for now. Thank you for your attention, and I'm open for questions.
Thanks, Lukas. Presentation is now open for questions. Yeah, please.
Will we cover such examples in the workshop tomorrow? Or that's too advanced?
Well, currently this branch of development is only existing on my machine, so we will be working on a production-ready software and not something that I developed over the course of a year. Yeah.
Web page, I see a tag to make Julia code as well. Would they do it under Julia framework? Yeah.
That's the nice thing about modeling. When we do have the template, it comes down to it's called user-defined language specificator. It comes down to, okay, I want this output to happen like this, and then you can just export it in Julia. If you're taking part in the workshop tomorrow, you will see that it can be handled quite easily. And yeah, it's envisioned that we do it as well in GAMS, Pyomo, and Julia.
So if you look at the GDP side, then most is happening at the moment on Julia, as a matter of fact. So the Julia GDP package is the most advanced, and the second most advanced is the Pyomo side. So those are the two competitors. The external function side, the part that we need for including the thermodynamics, is a bit better documented on the Pyomo side. So we started with that, and Julia's on the list.
Documentation, I'm assuming Julia, it's not. Yes.
Let's see.
Good. I think we can thank Lukas one more time. All right, one more presentation before lunch, and